All right, so now we'll get started. And as I said, this is the first flow. It doesn't get any more elementary than this, but there are some math here, and they may be hard to read, but I'm going to recite it as we go here. So there's two signal sources. One will be our baseband or uh, our information that we're going to modulate, that'll be modulating. And I've got that in this top signal source, and it's set for a frequency of 20 and an amplitude of 1. This is a real output rather than a complex output. I'm sure Steve will like to know that. So we're not dealing with two waves here, complex waves, complex numbers with that 90-degree offset. Now that will come back in, but right for now, this is a mix or a multiply of two real values. And so the second block is also a real, you can tell by the color of the output port. It's not blue, so it's not complex. It's real values coming out of here. And it's set for a frequency of 1,000 hertz, 1 kilohertz. And this would be our carrier. So underneath this block, which might be hard to see, it's hard for me to see, is M of t. So this is our transmit of our modulating signal is equal to AM, which is amplitude of cos 2 pi FMT. And there's some terms over here to the left. So M of t is the modulating signal, or we could call it baseband. Call it audio if you want for this demonstration. C of t is the carrier signal. It's really sub M. Amplitude of modulating signal, so it's set to 1. A of C is the amplitude of the carrier signal, that's also set to 1. And then FM is the frequency of the modulating signal, which is set to 20 hertz. And FC is the frequency of the carrier signal, which is set to 1 kilohertz. It's kind of not really realistic real world parameters, but they're good for demonstration purposes. Now, after the mix, we're going to have basically this formula. The signal to transmit is equal to AC plus AM cos 2 pi FMT times cos 2 pi FCT. And you'll quickly see that demonstrated. You probably have seen this in books many times and you're very familiar with it. We'll have our familiar throttle in here because we don't have a hardware device to limit the flow or the samples moving across here. And then we have a time sink here. So let's get this going. We stop this. We can see this is milliseconds across the bottom here. So these are running. Let's get over here where we can see the marker. So they're running, there's 21 milliseconds, there's 22, there's 23. So that's 1 millisecond apart. This is the millisecond scale down here. And 1 millisecond would be uh, 1/1000th of a kilohertz. So we're right on the money there. But notice the envelope. And to get a full signal, we would have to start this again. And out here like this. And then we would have a full cycle of the 20 hertz that's modulating like that. So it's ranging all the way from +1 to -1, as is this carrier signal. And we'll see this easier here in just a moment. So I created another sketch here so that we can look at this without having to move and put all these pieces together. So here is the very same, got them flipped upside down here, but basically this is the carrier on top. This is the information or baseband. And so what's happening here is that we've got three inputs to the time sink so that we can see all this good stuff. The first um, graph is going to show us the carrier. The second graph is going to show us the baseband. And then the third will show us the multiplication product through the throttle. So we'll see both of the signals mixed together and the resultant modulated wave. Now I've got a constant block that's disabled right now, and there's a reason for that. So we'll get to that here in just a moment. So we'll go ahead and get that started. Scale, and then I could use a scale. Okay, so if we, let me shrink this on the Y a little bit. So now let's take a look at what's going here. I want to open up the X. And of course, you got to start it again to do that. So the blue is our carrier, and we could check that out again by just looking at its periodicity. So 17 milliseconds, let's see, 17.0, that's basically 18, 19, and so forth. Here, the red signal is our baseband, and the resulting modulation is the green. So we can just chop some of this up. We can turn off the carrier graph, and now you can see a little bit better what's going on with the red baseband, which once again is fluctuating around a value of 0. And so is the modulation, and so is the carrier. Now, observe this, that the multiplication might be best to look at coming down right here like it is. So basically, it is multiplying the value here on the baseband signal times the value of the carrier, and it arrives right here. Say that right, because this is the signal. It's actually negative, but this is the other side of it, the symmetrical side of it. So basically, this value is being multiplied by the corresponding carrier, and it's going to reflect a result that is always less, except for these cresting peaks. It'll always be less than the carrier, the full carrier. This is a good illustration of how we end up with the modulated signal, which is showing here. It illustrates the multiplication. Now, one problem is that you might have noticed that the modulated carrier is falling below 1, and anything below 1 is not going to be good for the transmitter. So we're going to basically just add 1 to it here, which will cause it to come up above 0, and it'll rotate around 0.5. So we'll have to take this wire out. Let me get to the keyboard now. This wire out. This. Okay. So now we have just adding 1 to this, which will raise it on our graph, then going through the multiply and so on and so forth. So let's see the result of this. Oh, you can see without me even stopping it that, well, actually it's moving about a point at one. So there is a fluctuation between 2 and 0 now on the modulated wave. That would also go for 0 to -2. Out far enough, we'd find and be able to confirm that the red baseband signal is modulating on 50 milliseconds, which is our 20 hertz signal. Now, what I chose to do here, I'm not sure it's the best thing to do, but I wanted to divide by two so that I could take the modulated signal up. And so that's going to be in this right here. And so here is well, let's go back. This constant's required, and we didn't talk uh, about everything that it's doing, but one thing it does is it makes sure that there is a carrier when there's no signal source. You can't tell that right now, but when we get to the microphone demonstration, then it will make more sense. If you don't have something, then you're going to into this multiply. You're not going to have anything, and you're not going to have any carrier even. So because we have a simulated source here and it goes through this, it looks the way that it does instead of a modulating, like an audio waveform. This also shows up in the formula. So there is at least that constant of one is present in, if you look in Wikipedia or you look up other fundamental descriptions of AM modulation, there's always this one being added in. Now let's go over here. This one seems to get much more complicated, but what's going on here is there's a frequency sync for one thing. That's on a half, so you're only going to see the positive side, and that's done right here, spectrum width half. And then here's my divide by two. So I brought in a source of two and a divider, and then just took the output here. Now I did add a gain control here. This could also be called modulation depth or a ratio of how much modulation we're applying as versus the carrier. That is also in some of the formulas. So you'll see these two blocks, the modulation depth control and always a +1 here. But I did a divide by two, and here is the result. Still using a signal source. Okay, now we've changed the signal source, by the way, to 500 hertz. That's important to note. Now, this wave has a little funkiness to it, but basically it's got now the baseband fluctuating between 0 and 1 and the um, carrier between 1 and -1. Things in the way here, sorry. Trying to get down to this. So if you notice down here in the frequency spectrum, I did kind of take a note of this when I was playing with this, that when you start to overdrive with this mic gain, you'll notice that you have reached the sidebands have reached the level of the carrier. That's what you're looking at here. So there's our 1000 hertz carrier, and there's the one sideband at 1500 and one sideband at 500. But as we raise this, you see right about at a value of 2, the sidebands are almost level. I guess I can get this right on 2 if I work at it hard enough. There's 2. So right here, all 3 of these are at the same level, 20 down, and the we're rotating around this point right here with the baseband signal that's going out. Let's turn that off and just look at the modulated signal. This is already looking a little bit distorted to me, but when we go further, you're way below -1 here with the baseband, and this would result in a distorted signal. So if we go all the way to 0, then we should have a flat line, and we do. There is still a carrier present, and that's because of our constant that we put in there so that we got some kind of a carrier. And you can see it down here in the frequency spectrum. Let's see if I've got anything else noted here. Um, Next, I wanted to demonstrate the removal of the source and insertion of microphone. So we can do that a couple of different ways, but let's do it this way. Let's disable this, let's enable this. Now let's respect our sample rate. So you notice that we started this one with a sample rate of 48K, and it was because I knew we were either headed to a speaker sound card or we were going to use an audio source, such as a microphone. So I set it up for 48K. You could use a lot of different values there. That's not a golden value. Typically on your radios, you're going to have to use something in the mega samples. Which you'll discover if you take on the challenge of the homework, which will be to convert these to real radio flow graphs. But right here, we've got the microphone, and I have an external microphone here. My laptop microphone is just a total pain to use. I never could even figure out where it was on the laptop, but it works pretty good with an external microphone. So let's get it going. Testing, 1, 2, 3, 4, 5. Okay, so it seems to be uh, modulating from my audio. Let's see what we can do about trying to look at this a little closer. So take away the carrier and speak into the microphone, and we could get this to slow down enough that it stands still somewhere around in there. So still using 1000 hertz as the carrier, and let me see if we, no, didn't do that one. Okay. Well, let me just play something that's recorded. You can watch, and I'll adjust some of this around. I did record this earlier so that I wouldn't have any screw up, because you know how that goes. Um, every time I try to do something in real time, something breaks. Oh, just got to find it. This will be Carl Sagan speaking, and his famous pale blue dot that was taken by I guess it was Voyager camera that was out there passing Saturn or someplace where they was able to look back and detect the fine little tiny blue dot. There, the audio, let's be sure I've got that set correctly. See if this will come across. Seem to be playing. Try that again. Well, then we'll make an attempt at a real-time demonstration. Can you guys hear that?
We're not hearing any audio come through here. We see it modulating on the screen, it looks like. We don't hear anything.
Okay. All right, I apologize for that. And the audio is really loud in my ears. Okay, that'll be it for another day. And maybe we can make do with that with another video recording. For some reason, that video is not playing when I started where I recorded it before. All right, before we leave this subject on to the other one that I wanted to talk about today, I do have these other flow graphs, and I will put these on all of them. Well, these I will put on the NTMS website. This one is it's just a clone from what we've just been looking at. Um, and I've got some explanations here that I didn't have on the previous graphs. And it takes and the audio source, which is a microphone, and you can see the signal source has been disabled. It runs through the mic gain, multiply, and then the familiar one constant that has to be added. This divide by two that I've put in, and then three different graphs in the time sync, the baseband, the carrier, and the multiplied modulated wave. And then this block we showed last week is just a fancy way of not having a line that connects all the way over here. So as long as you uh, publish to an IP address that you match here on this subscription over here, the signal will go across there, technically on TCP. On input here, there's a couple of important things that happen. One is that it goes through this filter, and this filter can perform multiple um, functions here, frequency translation, filtering, and decimation. I've got a variable set on the decimation because what I was trying to do here, which I think I improved upon on another graph, but basically I was trying to take this 48 kilohertz that's coming out of here with this 1000 hertz carrier and virtually eliminate this 1000 hertz carrier by dropping down the sample rate here to go through AGC in this complex to mag block. And it seemed to work pretty good because what would happen on the output over here, especially, turning on an audio sync, is you'd just be overdriven with this 1000 hertz carrier, which we've said before. Of course, it's not realistic for radio. This would be something like for ham operators, you could use 432 or 902, 1296, but we'd use some other value other than 1 kilohertz here. This being an audio tone, as a carrier, it didn't make sense, and it would come through this audio sync. But when I did this decimation, apparently it dropped below this bandpass filter. I did not look at that real close, but either that or something through these three blocks caused it to be suppressed greatly. But I then still had to multiply back up by 16, which is how I got back to 48 kilohertz for the audio sync. I think all three of these blocks deserve a lot more of attention and understanding exactly how they work. This complex to mag is pretty important. There is a block called complex to phase also, so that you can separate the magnitude and the phase, which are going to be some of the subject that we're going to cover next. But the important thing here is that this is the demodulator. And in fact, one extra credit homework item might be for somebody to replace this with an AM demodulator, because there is a block for that, and note the differences and be able to tell us how that is different. But this turns basically this complex value back into a real signal and recovers the original signal that was formed up here in the top section. Graph that's here is virtually the same, except that it's been right here. The decimation is 1, and this is where I discovered this 1000 hertz was just driving me out of the room. Now, can you change that to 902? Sure. That will change, definitely change some things. The graphs will get very busy because that's such a high frequency, but you certainly could. But this was the answer to eliminating this 1000. Go back to the first here. These formulas you will see if you stare at them for a little while, they're really not complicated. The thing that kind of came to me as I was, writing this up is that a lot of the functionality is really hidden in here. And this is a learning tool. So knowing a little bit about the math, the Python, the C++ that's actually making this signal is important. But the math is relatively easy. And as we saw last week, that we can just add two values together, the I and the Q, and get a third signal that is the result of adding the other two. And that's all this is. And when you get down to it here, there is a multiply here. But what is multiply but just a lot of adds? Okay, now I want to move into this um, idea that we started with for this uh, follow-up, I guess you'd call it, although I think we've been having meet clinics as we go. But let's take and start with complex number and end up with a real number. And that's what happens if we're going to transmit. Now, I do want to say that taking two values that are complex numbers and turning it into a transmittable signal with a certain magnitude and phase is done in the SDR radio. But knowing how it happens is one of the reasons, I think we should be doing what we're doing. And so for that, let me see if I can get back to the glass and start on some drawing. All right, so let's draw. Well, tell me if you can see this. So this is our complex plane. And we would call these, let's say that each of these points is one. So this is positive one, this is minus one, and this is minus one, and that's positive one. And we want to pick a point out here that we want to transmit. Now, it would just be a moment in time, but I would argue that whatever you can graph here and whatever you can understand, it just goes around and around. And so understanding how a complex number turns into a real number is a worthy exercise. So I've chosen a number, and it is positive 7 and minus 0.4. I said 7 and minus 0.4. Now, we could locate that approximately out here by coming out to 0.7 on the positive and minus 4. And we might say it's that point right there, more or less. Now, this complex number also has a phase and a magnitude. Draw that by coming out from the origin. And so now we have an angle here, we'll call it theta. And we have a magnitude, which is the length of this vector from the origin at 0. Any question on that? The angle, whether degrees or radians, is measured from the positive real axis. So it'd be this chunk. So this goes over here. It's a different angle. If it goes over here, it's 359. So it's measured from, well, it's measured positive and negative too. So if it's up, if that vector is up here, then that angle is a positive, but it's measured from this chunk of the complex plane. Okay. I have on my notes here to mention, although I haven't seen it heard very much, but this is also known as a phasor diagram. And I would tell you right now that there are going to be times that we've talked about the imaginary component. In this case, it's this number over here. We've talked about that having subscript of I for imaginary, but it's also found to have a J as its identifier for that term. Now, I've got to introduce some math, and some of this should look a little familiar to you, but magnitude is the square root of really I squared and Q squared, but we could say A squared and B squared if we want to just have substitution parameters. So you should recognize that or begin to recognize that from last week because that was expressed then too. Now the phase, a little more tricky. If your calculator's not real friendly, the phase will be the arctan or tan reverse of, in this case, B over A. So if we carry this one, we'll have the square root of what? A squared is 0.7 squared, and that's 4.49. And B squared minus dot 4 is positive dot 16. Right? You almost do this in your head, which equals the square root of 65. Trying to get my other camera to work so that I could show you this on my phone, but of course that's not too hard to find this, and you would just take 65 and get the square root of it. Got my machine turned on into radians formulas. So let me hold on a minute and we'll do six. I won't carry it any further than that. Phase. There's 6 or half dozen ways to get that one with that arctangent function. On my calculator, I have to do the division first. And I have my calculator set up right now to return any expected degree slash radian slash gradients as radians. So if I want degrees, I have to specifically tell it I want degrees. So I have to hit this. I've got a Casio 300. So I have to hit shift mode setup and then select 3 for degrees. And now I'm in degree mode and I can say B, which is minus dot 4 divided by dot 7, and then take arctangent of that number, and I get this number. This is degrees. Get radians. I got to go back and tell it that now I want radians. That's a function 4. And then just do the same math. So it was minus dot 4 divided by dot 7. And then arc. radians. Okay, why am I doing that? Well, there's more to come. So I want to show you a couple other ways you can get this rather than going through all that pain. If you have Python, I just wrote it out like this. So import numpy, and then there's an angle. You just put in the complex number here, 0.7 minus 0.4j, which is the imaginary component. And then define a function magnitude absolute of z, and then you can just do this down here for the angle, I'm sorry, the magnitude of 0.7 minus 0.4j. So when we run that, you see down here we got minus 0.519 for radians, and we got 0.806 for magnitude. So you can do that, or you can go to this website, name of it's Alpha, Wolfram Alpha, and input your function, and it will spit it right back out to you like this. So there's our minus 0.519 radians. And then here's our minus 29.7 in degrees. And then when you look at this reference triangle in this angle, then you can see how the trig works out. It's a right triangle, which we knew, but there's that. Now, to put this to final use, because we're trying to reach the real number. And these that I'm going to put up here next should be familiar from last week, if you were here. Try to fit them in here if I can. Transmit. I use my phone as feedback so I can make sure that you can see what I see. And it fell on the floor. Okay. Rid of this. Okay. Transmit signal. Will equal. This is I and this is Q. Will equal I cos ft plus Q sine 2 pi. That Q, which will, in substitution, 0.7 cos 2 pi ft minus. Fortunately, I have to introduce one more thing. Not really, just reintroduce it. Okay, I'll have to eliminate this to make room. There comes the trig identity. So again, Ka cos x plus b sine x, a capital A cos minus phase. Now, we talked about that last week. Is the magnitude. Find that with what? We found that just a minute ago with the square root of I squared plus Q squared. And theta, the phase, we just found, which was a function of arctan. So now this guy becomes x of t dot whole, oh, sorry, dot 806 cos 2 pi plus the phase. That's a real signal. Now, the only place I could even get close to showing that in another way would be with the Python script we showed last week. This, recall, is just closest represented here. Well, by all of these, you're mainly looking at this one. And then this one as the result. Okay. So I, we know, is the -4 value. Is that right? No, I's the real. So that's 0.7. So I can get to 0.71. Now I is the blue wave here. Doesn't really matter. It's not going to be too interesting, that part. But the point is, these are just amplitude changes, not frequency changes, and not phase. So this one is our 0.4. Okay, that's as close as I can get. So the functions of adding the equation that I've got in pink up there on the screen, which you can't see now, is the result is this green dotted line. So what I would argue is at one moment in time on that complex plane, as that signal's rotating, we reach these values right here. This will be the resultant wave, the green dotted signal. That's proven in the math. So you can get a lot out of that little tiny dot down there, its magnitude, its phase, and how it plugs into these formulas to end up with a real signal, which is right here. The dot 806 cos 2 pi ft plus 0.519 is the phase. That's the magnitude in the phase. That's all I have for today, folks. What kind of questions do you have? Okay, if you have an SDR radio that can transmit, try your hand at converting the simulation flow graph into a real transmitter receiver combination. I'll do the same. And then if your rig does not transmit, if your SDR dongle is not a transmitter, then just convert this simulation flow graph into a real AM receiver and demonstrate the three frequencies that make up the AM signal. So the carrier and the two sidebands, be able to show those out. And before I leave, I'll look at this with you just for a moment, is that there's a lot of changes that have to take place here. Obviously, if you're going to make a receiver, you have a real receiver down here where this block is. Um, a lot of this would still apply here, but on the transmitter side, you have more changes. Um, you can still have an audio source here, but you don't need to have this signal source at all. This was what will be in your radio. So that would eliminate the multiply here as well. Your radio would go right here where this block is.
Jim, this is Don Westicott. Are you hearing me?
Yes.
Oh, good. Well, that works. I don't usually use this alternate microphone, but it's a question and an observation, Jim, if I could pose it. You were demonstrating during part of your presentation the process of if I could paraphrase it, over modulating the baseband. In other words, increasing the amplitude of that, I can't recall, 20 hertz signal so that it was above one. Am I paraphrasing that correctly?
Yes.
Well, these presentations are so fascinating because it makes me think. And at the same time, you were portraying the fast Fourier transform of that multiplied signal, the carrier plus the baseband. And when you were increasing the modulation and causing the distortion, if I could use your paraphrase, interesting enough, we did not see any other frequencies generated in the fast Fourier transform. And initially I thought, well, why is that? Because generally we think of distortion as creating additional frequencies in the frequency domain. But then, there was a very easily, simply answer that because we basically still have a linear system in the mathematics in that, multiplication of those two sinusoids or complex signals or baseband and that. So it kind of reminded me that the math works, but in reality, our mixers or our multipliers are not always linear devices. So thank you for that, knowledge passed.
That's a great observation. I did catch myself trying to inspect for harmonics, and I'll run this again. And I did see some unwanted signals down here. Problem is that this doesn't go all the way down to the noise. And so testing, one, no. not going to show up here, but I did find some harmonics out on one of these graphs when I overdrove it severely. So I think I've got some more to learn there, but that's a great observation.
Well, yeah, thank you, Jim. I have to think about that a little bit more because, um, even computers and our systems, have noise in them. There's always, we amplify something. I mean, everything has noise in radio communication. You can't get away
Sure.
from it. And so some of that frequencies we're saying are just noise uh, in the system, and whether it's noise from finite quantification of the amplitude levels in the math and how many bits we're carrying. I mean, it all comes into those artifacts that come on, and so yeah, it's a good homework exercise for me to go back and think about a little bit more if we have a perfect multiplication process. Do we, and then overdrive on the amplitude modulation sense with our baseband? Do we in fact generate additional sidebands? I'd have to think about and work out the math a little bit on that. But thank you, Jim.
I think we'll find that we can demonstrate that. I'll take that also as a takeaway to study and learn how we can demonstrate the overdriving. Now I know we do have an explanation for noise as it relates to these simulations because there is a point at which the size of the variables that are being used to pass into the FFT have some limitation, and there will be some what appears to be noise way, way, way down, like orders 10 orders of magnitude down from the signal. But there's easy enough to add noise if that's what we need. Uh, and there's ways to do that. There's a block for Gaussian noise, and we can mix that in and then have noise.
Yeah, I mean, there's so many topics to speak about, particularly when you can get into the idea of noise and a fast Fourier transform. We often forget that a fast Fourier transformer, or more correctly, a discrete fast Fourier transformer, because we're sampling data, so it's not a continuous sinusoid, and or just continuous signal. It's a discrete signal. As soon as we go into discrete fast Fourier transforms, we have a stumbling block that we can never perfectly uh, make that time domain to frequency domain transformation, except in the case that our sampling rate in the fast Fourier transform is identical to the frequencies that are in the highest frequency that's in the signal coming in. In other words, there's always there's always this little bit of system because of overflow in signal, and it comes back into Nyquist theory and the rest in that these additional signal and aliasing that things start folding over, and we start seeing additional signals that aren't there, and this is really the noise of the Fourier transform. What I'm trying to say, without a whole bunch of graphs and math, is fast Fourier transforms or discrete fast Fourier transforms aren't perfect, in their representation of what's going on with a complex signal. So that's a whole area of discussion, Jim, and I hate to belabor that. I'll turn it back to you. And I'm sorry I haven't explained it very well.
I have a comment also, if I can make it.
Go ahead, Bob.
One thing that's fascinating too about this is, GNU radio is kind of a cross between a simulator and a tool that you can use to build these things and actually employ a radio or create a radio or whatever you want to do. And this concept that you've shown in your graph here, where you're doing some portion of the signal processing and then you pass the signal through this digital block over to another receiver block is really a powerful thing, because what you can do essentially is split your radio across two different computers if your if your digital link is good enough between the two. So,
Sure.
or you could put a portion of your radio at your antenna up on your tower and then pass some lower level signals down to your inside your station to a higher power computer potentially to do even more work with it. Or you could even have multiple GNU radio instances that are all passing back to a single thing. So it's extremely powerful, and you've illustrated that well here too, I think.
Hey, Bob. Okay, you've hung around with me for more than an hour. I really appreciate your time and interest. It spurs me on, and I have a couple of things I'll take away. And then next week, we'll introduce an even deeper topic. The modulation schemes are worthy to stick around for a while. I also think that there's some interesting information in the overall architecture of SDR receivers, where my interest would be first, and the way that the design trade-offs were made. So I think this group of people that's here can go into those conversations, and we'll have a lot of depth or dynamic range to think about it and follow along with my limited understanding. But choosing a second IF, if you will, or the IF in the SDR radio versus the LO by itself would take up hours to talk about. And looking at the devices they've used, there's quite a difference between what's in the RTL, SDR, the HAC RF, and the Pluto. The approach taken is different versus how much will be digital, or I hate to even use that word because it's more like digitally controlled than it is anything to do with like sampling. So a lot more to be learned by me on that, and I'll share it with you, and we'll just keep going like we're going. But these are the fundamentals. We'll come back to these very core elements time and time again. So I'm going to turn off the thing and go finish up on another project for the XYL. Got to pay it ahead, guys.
Jim, can I ask you where that AM transmit receive flow graph is?
I haven't put it up there yet, but I will this afternoon, and then I'll make sure Steve. I'll send out an email to the group, but you and I do a lot of chatting on the side, and I can make sure that you've got it.
Thank you.
Sure.
Jim, if I could have 30 seconds, I've got to sort of regroup after my blunder of explanation of what I'm trying to talk about was principally spectral leakage. Could I have 30 seconds, please?
Sure.
Okay, to really clarify, my muddling through here a few minutes ago, what we're trying to do when we make a Fourier transform, or more correctly, a discrete Fourier transform, is do sampling of a signal in the time domain and convert it to the frequency domain. This this is what we commonly call the fast Fourier transform, or more correctly, a discrete fast Fourier transform. But we need to remember that if we do not start and stop the sampling at exactly the same point in the phase of the signal, okay? In other words, we have some complex signal and we start at time t equals 0, and then we take 512 or 10,024 samples, and then we stop and said, okay, that's our sample set, that's our discrete data points on this waveform. 512, 1024, some number of points. If that first point and the last point do not occur at exactly the same phase of the signal, and of course we have no knowledge of the phase of that signal. We're just taking random points separated in time. Then we have a phenomenon occurs that's called spectral leakage. And this is additional frequencies that are generated due to the discontinuity in phase between the starting point and the ending and the last point. And this generates all this discussion of different filters, Hamming filters, and associated with dealing with filtering that signal to eliminate this spectral leakage. And that is an artifact of this mathematical process and will appear in GNU radio. This same, and it will appear as noise on the signal. And that's kind of what I'm trying to explain, Jim. And I hope that clarifies my former bumbling around.
No, that's good. It's good that our tool is as close to reality as it can be. All right, guys, I gotta go hang in the second AI assisted birdhouse in the backyard, so the XYL can watch birds from multiple angles. And so I will see you guys later.
Sounds
Thank-
like a good way to keep her entertained so she's not thinking of projects. Good job.
Uh,
Thank you, Jim.
Thank you, guys. Thank you.